Okay, welcome back to this next video in our machine design series. We are continuing our discussion today of helical compression springs by talking about some failure modes. One of those is closure, and I should clarify that sometimes our springs, they need closure, just like you need closure when you end a relationship. Sometimes our springs need closure to do something called set removal or presetting, which helps the spring induce some residual stresses that are helpful to prevent failures later on. We're going to get into all that in a second. And then later we will also talk about another failure mode of springs, which is known as buckling. So this is what happens when the deflection becomes too large. Our compression springs might buckle and deform in a way that is unexpected. I wanted to start today by kind of revisiting where we left off. We were talking about the number of active coils, and I mentioned that you can find equations for these in table 10-1 in Shigley. I thought it might be useful to go ahead and put one version of that table in this video so you guys can see what that looks like. So this table shows how the type of end of our spring, it changes the number of coils and the length and the pitch. So some geometric parameters of our spring. And the different types of ends that are listed here are, first of all, we have plain ends, which is exactly how it sounds. We haven't deformed the ends, we haven't ground them. They just are as they would be if we took a plain helix and cut off the ends. Then we have plain and ground. So this is a plain end spring where we've just ground down the ends to be flat. And that is the type of spring that we drew up here. We can also have squared or closed ends, which is a spring that has been deformed at the ends to a 0-degree helix angle. So we've just closed off the ends by deforming those last couple of coils to square them off. And then squared and ground is a combination, of course, of the previous two. We've both squared the ends, so deformed the last helix or two, and we've also ground the ends so that it's nice and flat. Okay, and depending on the type of spring end that you have, you're going to have different equations to find the number of active coils from the total number of coils. So, for example, if I count that my spring has 15 total coils, and we have the same type of spring end as pictured above, so we have the plain and ground ends. Then to find my number of active coils, I can use the equation in that second line there, which says that the total number of coils is equal to the number of active coils plus 1, which means that the number of active coils is 15 minus 1, or 14 coils. Okay, so that's how you use this table. We also talked about the free length in the last video, which is the axial length of the spring when it's unloaded. And now today we're going to talk more about the solid length. So let's talk about closure. When all of the coils of the spring are compressed to the point where they touch each other. The spring has, quote, gone solid. All right, so let's see what that looks like. I'm just gonna copy this drawing from up here so I don't have to redo it all. Okay, so if I am compressing this spring and I'm pushing until the point where these coils are actually touching one another. Okay, so roughly looks like this. This height of the spring at which all the coils are touching one another, this is called the solid height of our spring, or the solid length. And F sub S is the force required to achieve closure. And then to check that the operating point of our spring is sufficiently far away from going solid, we define something called the, let me move this out of the way, fractional overrun to closure. Okay, because we don't want our spring to go solid typically during service. When a spring does go solid, it starts to behave like a solid cylinder, close to. Before then, it's behaving as a spring, and the deformation of the individual helix sections of the spring is what allows that spring to deform, absorb energy. But if the coils all touch each other, the spring goes solid, now we can't achieve that same amount of deformation. And so if we were expecting to absorb energy by having lots of deformation, then our analysis is thrown out the window. So anyway, we define the fractional overrun to closure as the force required to achieve closure, Fs, equal to 1 plus this fractional overrun, which is this chi symbol, times F max, which is the maximum force applied in service. So we recommend that this fractional overrun to closure is greater than or equal to 0.15 or 15%. And for those of you in my class, I would recommend that you keep track of these recommended ranges. That would be a very good exam question to ask you if the total number of coils, number of active coils, is within the recommended range. Okay, so with that, we have covered closure. Again, that's when all the coils of the spring are compressed to the point where they touch each other. And as mentioned at the beginning of the video, sometimes this is desired. We can perform a process called set removal, where the manufacturer will make the spring longer than it's actually needed and then compress it to its solid height, which sets the spring to the required final free length. And then since compressing the spring to closure will actually exceed the torsional yield strength of the material, this induces residual stresses. And those residual stresses are opposite in direction to those that will be induced in service. So this can be very advantageous in the case where you need high strength. So especially when we have energy storage uses for the spring or applications, it can be very useful. I would think twice about getting a spring with set removal if you are concerned with fatigue. Remember that the mean stress that's applied in or felt in a material in fatigue has a significant effect on the fatigue life. And so having residual stresses when you're concerned about fatigue can be disadvantageous. So anyway, think about set removal twice, especially if you have an application with a lot of fatigue, meaning a lot of load and unload of your spring. Okay, that covers closure. Now let's move on to buckling. All right, so compression springs can buckle when the deflection becomes too large. If you're familiar with buckling of straight beams, you know that if I have a straight beam, I'm applying a compressive load. If I exceed the critical buckling load, then my beam may deform sideways to look something like this. That's buckling. The same thing can happen with springs. And we will define, in this case, a critical deflection of the spring rather than a critical load, although you can use Hooke's law with the spring rate to come up with the critical load from the critical deflection. And it's equal to the free length times this C1 prime constant times 1 minus, parentheses, 1 minus C2 prime divided by lambda effective squared to the 1/2 power. Then we close these parentheses. Okay, so there's some constants in here that we haven't seen yet. Let's define them. C1 prime and C2 prime are dimensionless elastic constants. Which we can define using elastic moduli. So C1 prime is equal to Young's modulus divided by 2 times Young's modulus minus the shear modulus. And C2 prime is equal to 2 pi squared times Young's modulus minus shear modulus divided by 2 times the shear modulus plus Young's modulus, where these moduli values come from the material of the spring, which again you can find in table 10-5. For common spring materials. And we also have not defined this lambda effective yet. This is the effective slenderness ratio. If you've analyzed buckling of beams using Euler's buckling equation, there's a similar constant or variable that is used in that formulation. So this effective slenderness ratio is equal to alpha times the free length divided by d, which again, remember that's the mean coil diameter, not the outer diameter. And see previous videos if you need a refresher on the difference between those. And now we've introduced another new constant that we need to define. So alpha is the end condition constant. And this depends on how the ends of the spring are supported. So you can find these in table 10-2. For example, a spring that is supported between flat parallel plates. So, for example, a spring with flat parallel plates. So these plates do not allow for rotation of the ends of the spring. It's sort of like a fixed end condition. In that case, alpha is 0.5. Okay, and it varies for the conditions listed in the table between 0.5 and up to 2 for the condition where you have one end that's clamped and the other end being free. Okay, so something that we would like to understand is when we have absolute stability, meaning that there is complete resistance of the spring to buckling. And we have an equation that allows us to predict when that will happen. So absolute stability occurs when our free length is less than pi times mean coil diameter over alpha times 2 times Young's modulus minus the shear modulus divided by 2 times the shear modulus plus Young's modulus, close parentheses, and to the 1/2 power, or square rooted, same thing. So we would like to have absolute stability in many different scenarios where we want to make sure that we're not going to have this kind of horizontal, unstable deflection. And to achieve that, we just need to set our free length of the spring low enough. So you could think about a spring on a playground, the kind of horsey ride where the horse that a child sits on is set on top of a spring. That spring, by the way, has an end condition where one end is clamped, the other end is free, so alpha would be equal to 2 in that case. And we may want to ensure that we don't have buckling of that spring when a child gets on top of it. To do that, we just need to make sure that the free length of the spring is small enough that it is below this value. So whatever we come up with from this expression. You can think about that toy on the playground. If you make that spring too long, you could see there is a critical length where now instead of simply deflecting up and down, we're going to start getting potentially some buckling. Okay. And as another example for something you can try to calculate yourself at home, for a spring with squared and ground ends. So when you see this squared and ground ends phrase, you should already start thinking of that table 10-1 that we showed up here, right? This is gonna be your friend for finding all different parameters that we might need. Okay, so for spring with squared and ground ends, supported between flat parallel surfaces, the condition for absolute stability is free length must be less than 5.26 times the mean coil diameter. Okay, so I encourage you to take some time and try to plug in some values into this equation to get this same result given the conditions outlined in this example. All right, so that covers it for both closure and for buckling. And in the next video, we will talk about spring materials, and then we'll put it all together. We'll do a nice big long example designing a helical compression spring and checking for buckling and for closure under given loads. So thanks for watching. Hope you enjoyed it. See you in the next one.